right, let's do some more calculus. So here, this is saying, we started this yesterday, but I want to just make sure that you're good with this before we move on to something slightly different. On here, it says determine the intervals where the graph is concave up, concave down, determine points of inflection, or the coordinates of the points of inflection. Coordinates is important. You need an x and a y value. So whenever you're doing this, you should be thinking points of inflection, concavity. The first derivative tells about increasing, decreasing. The second derivative is all about concavity and points of inflection. So you need to take the derivative, but I'm going to rewrite this first because the chain rule is a little bit easier to do here than the quotient rule. So g prime of x is the first derivative. Wow. Then the second derivative is going to take a little bit more work, because do you see how here you could either rewrite this and you could say, well, this is negative 12x over x squared plus 3 squared, or you could do this as a product rule. And there are actually advantages and disadvantages to each one of these. If you do the product rule, I think the product rule in some ways is a little bit easier to remember, but because there's a negative exponent, you're going to end up putting a lot of things into a single fraction anyway that is a little bit harder. In this case, I'm going to just go with it and do the quotient rule. Plus, it's good practice. We haven't done it in a while. And say the bottom, the derivative of the top, oh, sorry, this is the bottom, times the derivative of the top was negative 12 minus the top, wait, bottom derivative of the top minus top, there we go, derivative of the bottom, chain rule, wow. So 2x squared plus 3, the first power, don't forget the derivative of the inside, over the bottom squared. Okay, so this all looks like a lot, but what I want to do with this is I want to figure out where is the second derivative equal to 0 or does not exist. For does not exist, I would just set the denominator equal to 0. X squared plus 3 squared is equal to 0. If I have something squared plus 3, think about this. This is like a parabola, but it's 3 units above the origin. It's never going to be at a place where x can make this equal 0, because this could never be a value of negative 3. So you could go through this whole process, but there's never a place where there's going to be a place where x can be equal to a number that would make this 0. Don't believe me? Keep going. Take the square root of both sides. You would end up getting x squared is equal to negative 3 when you got 3 on the other side. You can't take the square root of a negative number. Not okay. So I'm going to leave that alone, and I'm going to set the numerator equal to 0. The numerator would be x squared plus 3 squared times negative 12 plus 12x, because I'm just putting this together, negative, negative. I'm just going to leave all this mess here. And I want to know, where is this equal to 0? I could have put it on the other side too, but I ran out of room. Okay, we could do a whole lot of work here, and we actually can get this into, if you simplify this, into 36 times the square root of x squared minus 1. But what I could do, ooh, guys, this isn't that important, but I just want to make sure that you see my error. Do you see how we did bottom derivative of the top minus top derivative of the bottom over the bottom squared? That's not squared. This is squared. Okay, so we could do a lot of work with this and figure out that the numerator actually becomes 36 times x squared minus 1. It takes a little bit of work, but promise, here, look, I have lots of work there. If you're like, I'm not convinced, but it's there. But what I would want to do, and you can actually factor out an x squared plus 3, 1 from here, 1 from here, 1 from here right away. But what I want to do is actually just say, you know what if it was this whole mess? How would I find the zeros here? So negative 12 times x squared plus 3 squared plus 12x times 2 x squared plus 3 times 2x. If I graph this, I can see right here there's a 0 here and a 0 here. So one of the ways that I can do this is I can say second calculate, and you can go to 0. The left bound I can see is negative, so I'm going to push enter, going to the right. I'm waiting for my x to be, or my y value to be positive, because I can see that these numbers are changing drastically. Enter, enter, and I get x is equal to 1, which if you looked at the simplified form, you can get that also. Or, oh, this is over here. Whew. How about that? X is equal to 1. That gave me the, where I was on the graph. I didn't even quite realize it. I was on this side. You can zoom out if you want to be able to see this a little bit more clearly too, but it was on this side, so this is the 0 that it gave me. The other thing that you can do, and particularly in this graph, it's a little bit hard to see whether I'm going from negative to positive or positive to negative. I can kind of tell, but it's harder when you're doing left bound and right bound. The other thing you can do is if you go to y equals and you put y2 is equal to 0, if you do second calculate, I feel like I just hit something weird. Make sure nothing's there. Oh, see, I did. I knew I did something weird. Okay, y2 is equal to 0. If you go to second calculate and I do the intersect, because now I have this line, y is equal to 0. It's still graphing it. You can do second calculate, intersect, first curve, second curve, and then when you guess, I'm going to get close to this value. Hey, look at that, x equals -1. So just a little trick if you're ever trying to find like what the 0 is, you can always either find the 0, do second calculate 0 and do the left bound and right bound, or you can make the second y2 be equal to 0, second y2, I don't know what I'm talking about, y2 equal to 0, and then you can find the intersection point between the two. Okay, and this one we could do by hand, but again, I just need more paper and need more room, and I didn't have it. Okay, so here I'm going to make my box, and I'm going to say, or my table, this is x, this is g double prime. I'm going to go from -infinity to -1, -1, -1 to 1, and 1, 1 to infinity, because I knew something important happened where the numerator was equal to 0, meaning the second derivative was equal to 0 at -1 and 1. Same thing that we used to do before when we would substitute in, we'd pick our favorite number in this interval, substitute into f prime or g prime or whatever it was. Now we're going to do it in g double prime. So I'm going to say -infinity to -1, I don't know, -100. The denominator is always going to be positive, so all I have to worry about is the numerator. And I'm kind of going to cheat here because I told you this simplifies to 36 times the square root of x squared minus 1. If I put in negative, I don't know, let's say -infinity x squared, or -500. -500 squared minus 1 is still going to be positive times positive, I get positive. Same thing if I put in positive 500. 500 squared minus 1 would be positive times 36, positive. If I substitute in a number like, let's say 0, 0 squared minus 1 would be negative times 36 is going to be negative. That means g is concave up on the intervals, -infinity to -1, and 1 to infinity. And the reason is g double prime is greater than 0. I'm going to be writing out here too because I don't have that much room. G is concave down on the interval -1 to 1. And the reason is as g double prime is negative or is less than 0, or however you want to write that is easier. And I'm going to just go up to the top just so I can write the one thing. I'm going to say g has point of inflection at, and I need two values. This is always back into the original function, but g of -1, it asks for coordinates, so I'm finding the actual point. G of -1 equals something, and g of 1 equals something. And the reason is as g double prime changes signs. Or you could say as g of x changes concavity. So as g double prime changes signs, I already justified this. I showed it in my work down here. I did lots of other things, but at point of inflection at g of -1, the last thing that I need to do is just go up to my original function. -1 squared plus 3 would be 1 plus 3 is 4. You can say 6 over 4 if you wanted to rewrite this as 3 over 2. You go for it. Same thing if I put in 1 squared plus 3 would be 4, 6 over 4. If you said 3/2, that would be totally acceptable. But these are the points of inflection. Okay. Here's another thing, and I already wrote part of this in. The second derivative test is not actually about concavity. I actually don't like the way that this is named, but this is another way to find relative mins and maxes of the original function. And I just need you to think through this for a second. So I already wrote this down. If f prime of c is equal to 0, so the slope of the tangent of a function is equal to 0, and f double prime of c is less than 0, then f has a... Okay, so let's think about this. Let's say f double prime of c is less than 0. That's talking about all about concavity, so concave down. So I want you to draw that. I don't know whether f prime is increasing or decreasing, so I'm just going to draw it like that. F double prime is less than 0. This means f is concave down. F prime of c is equal to 0. Well, where is that happening? It would be right here, where the graph is neither increasing or decreasing. So this is a graph of f, and it's neither increasing or decreasing. So this is f has a, this would have to be a relative max. So you really just need to think through this more than memorize it. It's more like, okay, well, does this make sense? If f double prime is greater than 0, think about it. Concave up looks like a smile. F prime of c is equal to 0. The only place where that happens would be here. This is on the graph of f. F has a relative min. This is the second derivative test. Let's use it. Okay, use the second derivative test to find all coordinates. So the second derivative test said that I have to figure out where f prime is equal to 0 in both of these. So let's do that. So in this one, f prime of x is equal to 4x to the third minus 12x squared. And I want to set this equal to 0. If I do that, let me factor this out. So I would have 4x squared that I could factor out. And I would be getting x minus 3. So at x equals 0 and at x equals 3, that's when f prime of x would be equal to 0. And then the next part is f double prime, is that greater than 0 or less than 0? So what I need to do is find f double prime. F double prime of x would be, I'm going to go up here and just use the power rule, so this would be 12x squared minus, this would be 24x. And I actually am going to factor this one, not because I have to, but because it's going to be easier to see whether my values are positive or negative if it's factored. So I'm going to factor this out, and this would be 12x, I'm going to factor out x minus 2. All I need to check then is whether f double prime of c, in this case, 0 and 3, are they going to be positive or negative? Okay, f double prime of 0 would be 12 times 0, 0 times negative 2. That's still 0. That's not positive or negative. That doesn't tell me anything. What about f double prime of 3? 12 times 3, 3 minus 2. This is positive, positive. Hey, I got a positive. That's nice. So what I'm going to say here is, and you could do 3 minus 2 is 1. 12 times 3 is 36. I know I'm writing into this box. That's okay. But what I'm going to say, my justification, and I want to even think through this without using the rule. First, if I have a function where f double prime is positive, which means f of x would be concave up. I don't know increasing or decreasing. And I know f prime of 3 equals 0. Hey, that looks like a relative min to me. I don't know why I drew it kind of crooked. There we go. So I'm going to say, by the second derivative test, f has a relative min at, and I need to see, does this say, this says coordinates, so I need to actually find the value. F of 3 equals, I'll find that value in a second. And the reason is, as f prime of 3 is equal to 0, and f double prime of 3 is greater than 0. So the last thing is just going back up and saying, well, what is 3 to the 4th minus 4x cubed plus 2? 3 to the 4th minus 4 times 3 cubed plus 2, and I get negative 25. Ta-da! We did it. Let's do one more. Were you hoping that it involved trig? It does. Let's even switch to a different color because I can. Okay, in this one, so the same idea. If this is saying the second derivative test, it's confusing because second derivative is all about concavity, but the second derivative test actually tells us relative mins and maxes. It's just something weird to remember. But this is only saying on the interval from 0 to 2 pi, so it's nice. We don't have to find all the places where the derivative is equal to 0 because that would be an infinite amount, only 0 to 2 pi. So find the derivative. F prime of theta is negative 2 sine of theta. And this is where people mess this up sometimes. Don't let this be you. The derivative of negative theta is negative 1. Think about it as an x instead of a theta, and then that's helpful. The derivative of x is 1 or negative x is negative 1. Same idea here. And then I'm going to say, where is this equal to 0? Negative 2 sine of theta minus 1. Add 1 to both sides. And then I would get negative 1/2 is equal to sine of theta. Okay, here's where you have to think through some trig. This isn't everybody's favorite. Maybe it's not your favorite, but it's okay. So you're going to be thinking, or I think there's lots of ways. Maybe you're thinking about the unit circle and you're like, where is sine of theta equal to negative 1/2? In my mind, what I'm thinking is I need a triangle that has the 1/2, and I know that that's the one that has 1, 2, square root of 3 on it. And then this would be a 30, 60, 90 triangle. 30 is the smallest angle, smallest side, 60 is the next across from here. This is hard to see. That says pi over 3 and pi over 6, which is really, really small. I need the 1 over 2, so I'm talking about sine. Sine is opposite over hypotenuse. So I know sine of pi over 6 is 1/2. And you might be saying, well, hold on, this is negative 1/2. All is positive here. Sine is positive here. I need to be thinking about, okay, pi over 6. What would be in this quadrant and this quadrant? I'm going to have two different values. So if this is 0 and this is pi, pi over 6 is here. So that would be positive, so that isn't going to work. 2 pi over 6 is, that's here. I'm going to go through what's in my head. Pi over 6, 2 pi over 6 is 1/3. That one doesn't count. 3 pi over 6 is just pi. That one doesn't count. 4 pi over 6 doesn't count because that's 2/3 pi. 5 pi over 6 would be in this quadrant because it's almost a pi. It's almost 6 over 6 pi. That doesn't work in this one. What are the other ones? 7 pi over 6. Let's try that one. Hey, that would be down here. That's a good value. So one of my values for theta is 7 pi over 6, that I would get a negative 1/2. The next one, if I keep going and I go through this trend, I'm like, what could be in this quadrant? 11 pi over 6. Because that would be like almost a 2 pi. That's almost 12 pi over 6. So in this one, I have two different values that I'm going to be using here. And what I need to do is I found the values where f prime was equal to 0. What's the next thing that you do? Find the second derivative and get positive or negative. So the second derivative here, if my derivative was negative 2 sine of theta minus 1, the derivative of negative 2 sine of theta is going to be negative 2 cosine of theta. The derivative of negative 1 is just 0. So what I need to know is f double prime of 7 pi over 6. Is this positive or negative? F double prime of 11 pi over 6. Is this positive or negative? Okay, so I already have negative 2. And then I'm thinking cosine. Okay, cosine of pi over 6. If I have cosine of just regular pi over 6, I'm not worrying about negatives at all. Cosine is going to be square root of 3 over 2. It's adjacent over hypotenuse. Same thing down here. I'd have negative 2 square root of 3 over 2. Because I know my reference angle is pi over 6 in both of these. Here's where I need to go back to cosine of pi over 6. So cosine of 7 pi over 6. 7 pi over 6 is in the second quadrant where only sine is positive. If only sine's positive, that means cosine is negative. Negative times a negative is a positive. For 11 pi over 6, it's in this quadrant. Hey, cosine's positive, which means square root of 3 over 2 is positive times a negative is negative. So I can say by the second derivative test, f of theta has a relative max. Let's actually figure out what this is then. At f of something. Okay, let's think which one's a max, which one's a min. We know that both of them, the derivative is equal to 0, so now I need to look at the second derivative. Positive means f of x would be concave up, which means there's going to be a relative min at 7 pi over 6. Concave down is when f double prime is less than 0. So at 11 pi over 6, and I'm going to figure out that value in a second. By the second derivative test, f of theta has a relative max at f of 11 pi over 6, and my reason is, as f prime of 11 pi over 6 is equal to 0, and f double prime of 11 pi over 6, f double prime was less than 0. This is really wordy. You're going to make so many friends. By the second derivative test, derivative, I almost forgot to spell that. F theta has a relative min at f of 7 pi over 6. This is the one we just talked about. And the reason is, and I'm going to find out whatever that value is in a second. The reason is, as f prime of 7 pi over 6 equals 0, and we also said minimum because f double prime of 7 pi over 6 was positive. Whew, so much, but the last thing that we do is go back to our original function, and we're substituting in 2 cosine of 11 pi over 6 and 7 pi over 6. So if I do this, I'm going to say, actually, I'm going to do it over here. I'm going to write this in a different color anyway. So f of, let's do 11 pi over 6 first, because that's what I wrote first. That would be 2 cosine of 11 pi over 6. So I'm just going up here. Minus 11 pi over 6. Technically, when you get to this point, anything that you can put into a scientific calculator, including cosines, if we're just talking about what the final answer is, like what the coordinate is, you could put that coordinate right here. But let's just go a little bit further just to make sure that we're on the same page as what cosine is. Remember, cosine is adjacent over hypotenuse, so this would be square root of 3 over 2. So 2 times square root of 3 over 2 minus 11 pi over 6. If I'm talking about 11 pi over 6, I'm looking in the fourth quadrant where cosine is positive. So I'm just going to keep it as this, where I have 2 over square root of 3 over 2. I guess the only thing I might do is that. So I get square root of 3 minus 11 pi over 6 as my point. If I do the same thing with f of 7 pi over 6, I'm going back to the original function, 2 cosine of 7 pi over 6 minus 7 pi over 6. 7 pi over 6, we just said that this is still going to be the square root of 3 over 2 because pi over 6 is my reference angle. Oops, sorry. But I need to consider, is this going to be positive or negative? And 7 pi over 6 would be just a little bit past pi. Think about like pi and another 6, where only tangent is positive. So this is going to be negative. So the 2 still cancel out. So I'd have negative square root of 3 minus 7 pi over 6. Okay, good news about this one. Not only are we done, but if you show this at your lunch table, I know that there are only like a couple people there right now, but if you show this at your lunch table, you're going to have so many friends. It's going to be awesome. Okay, deep breath. Thank you for being you. Think about it. If this wasn't all like the trig functions and really scary, think more back to this for a second. Are you okay with this? Do you understand that if the first derivative is equal to 0 and the second derivative is either positive or negative, how to figure out if I have a relative max or relative min on the original function? Yes, you can go back and still do that original table that you learned like, I don't know, more than a month ago now. You can still do that. That's okay. But there are going to be some times where this one is just a little easier. Okay. Thanks for being awesome. Thanks for working. I appreciate you. I hope you're well. Bye.